This week we're going to go full force into Chapter 3 on the spectral representation material. I put up an assignment sheet over the weekend. I put up an example sheet, which I also handed out, which we'll start working on today, which is based on this material. Also over on the website, I've also put in the link to Lab 3. And I've also put in a histogram sheet that you can just take a look at that sees what the score distribution is from the first homework and the first quiz. I've met with my grader this morning and went over some ground rules, so I think that will be converging in that area. I'm sure that a lot of you are going to be wrapping up the lab this week. I mean, you haven't written the lab up yet, right? Problem 5 and Problem 6. Problem 5 is pretty much just following the instructions. Problem 6 is a little bit more detailed, but Problem 6 is where I gave you that sheet last week. That's this note number 2 sheet in particular. So Kyle is available to support you as you finish writing up your lab. I can handle questions. Don't put it off, though. There is a pre-lab that goes along with this second, with the lab number 3, and lab number 3 is actually a very short lab. It doesn't have nearly as much steps to it as lab number 2B did, but it's only 1 week, so we'll be on to something else after this. This one begins the hearing experiments where you're going to be bringing headphones and listening to things. So you'll be listening to some sounds and probably some of the same sounds that, if things go well here, we'll listen to today. But you'll spend more time playing around with them. So yet another cable to plug in. But before we get into listening to any sounds or talking, we're going to talk about spectral stuff. One other little thing that last Wednesday kind of threw me off. At the request of some of the graduate students I have, I've since added this link called Office Hours. So this gives you a perspective about what I'm doing during the day, how I have office hours padded around this class, either side of it. And you can see where my other classes sit. And if that looks like I have a lot of white space, look again, because that's a 12-hour plus interval that I have on the board right there. So it's not like I'm sitting around idle. Actually, starting next week, I'm going to be filling in some more of these time zones because I'm on a review committee for the faculty across the campus that I have to start doing my active duty of 4 hours a week plus. So at least lets you know how things fit in and how you could request times for after hours. I mean, non-regular office hours. And I say that because I'm here a lot, but I can't make absolute guarantees because of other things that I'm involved with or can be called away to. So before I get rolling on this, again, because we started a little bit last week, do you have any questions? Yeah?
Did you grade the quizzes?
No. I've looked at them. I wrote up the solutions. The solutions are already posted. I saw that I made the quiz pretty easy, I think, so I'm hoping that everybody got a 10. I looked at it and I said, oh, I think maybe I made this too easy, but we'll see, right? Hopefully by Wednesday we'll have both the homework set number 2 back and I'll have the quizzes done. I talked about donations when the guy from TI rolled into my office. So as we had started on this last week, spectrum analysis applies more importantly to the case where we have multiple sinusoids. And this is what you were doing in the lab. In the latter part of the lab, you're working with this synthesis sine function where you synthesize multiple sinusoids together, and that will be carried forward into this next lab. So in this instance, see, got the wrong color up there. All of the f sub k's in general are going to be different. They don't have to be different. And in particular, in problem number 5 of the lab that you're wrapping up on, they asked you to use the synthesis sine function to generate a single sinusoid in the phasor addition mode, but you just get to put in the same frequency over and over again. So you've got flexibility in that function that you created in the lab. But in general, what we're talking about here is having a superposition of a bunch of different sinusoids, all at unique amplitude, frequency, and phase, and then also a DC component, something that raises and lowers or biases the waveform up and down. And of course, in terms of real or complex sinusoids, this second form down here is equally valid, as we've already learned about taking the real part of a complex sinusoid gives us just the cosine term. So that's equally valid. What we'd like to do with the spectral representation is get an alternate view rather than just seeing a time waveform. I think you already know from the second sign-off in the lab, when you superimpose a couple of frequencies, you start to get just a squiggly waveform. And if you look at that squiggly waveform, you can't necessarily see with your naked eye, oh, there's a 100 hertz component, there's a 250 hertz component. That's what you did in the lab. Or maybe there's 1,000 hertz and a 10,000. You can't really see that in the time domain plot, the plot of the waveform. But in the spectral domain, we can see things that we don't see in the time domain. So electrical engineers in particular, when we do signals and systems work, we like to have alternate viewpoints so that we can see things with basically another set of eyes. So we have our time domain eyes that we've been playing with. We're now going to investigate spectral domain eyes, and the lab this week definitely drills on that. So the way we get at this is this graphical representation where we use Euler's formula, Euler's inverse formula is how we get at our spectral representation. There's other ways of doing it, but this is the way that's most common, the way the book chooses to do it too. We break each cosine up into a positive spinning frequency and a negative spinning frequency. So we have an e to the plus j term and an e to the minus j term. And we know from Euler's inverse identity that for example, is cosine theta. So that's the basis for expanding things out. We have a cosine that breaks apart into two complex sinusoids, one that's spinning clockwise and the other spinning counterclockwise. One that has a positive frequency, this one has the positive frequency, and then this one has the negative frequency. And then when we do this breaking of the terms apart, we also break apart the amplitude and the phase into a complex term x sub k, and that's the same x sub k that we have up here. Its magnitude is ak and its phase is phi k. So if we look at what characterizes this waveform in the frequency domain, we can look at all of the parameters inside of that equation 3.2 and see that we have one parameter set is just what's going on with this DC term, and that has the fact that it's a frequency at 0 and an amplitude of x0. When you go ahead and look at the first term in the sum, when k is equal to 1, we have a frequency f1, and then we have a coefficient x1 over 2, because we're taking that 1/2 from the Euler expansion and lumping it in with the coefficient. So we have x1 over 2 at plus fk, and then from this other term over here, from the negative frequency term, we have an x1 conjugate over 2, and that's at the negative frequency. And then so on, going down through the list of all the possible values of k until we get up to, x of n, till k gets up to n. Then we have the final pairing. We have fn with amplitude xn over 2, and at minus fn we have an amplitude of xn conjugate over 2. So we use all of these pairings in here to motivate the spectral plot. And the spectral plot idea is that we're going to plot something versus frequency, and we're going to indicate at different frequencies where we have a certain amplitude or where we have a particular phase associated with the coefficients x sub k over 2 and x sub k conjugate over 2. So if I was to try to scribble all that in here, we can put up a couple of different plots, and one is the magnitude plot. So we'd have a spectral line like this at fk and f of minus k. And then we have an angle plot at fk and minus fk. And that extends for all values of k, of course. So this gives us this spectral view that we can look now at the frequency axis, which is the horizontal axis, and look up where we have lines popping up telling us in our signal where we have frequency components in the embedded sinusoids, whether they be at 500 hertz, 1,000 hertz, and so on. This is called a two-sided magnitude or a two-sided phase spectral plot. Two-sided is because it's always plotted on for both positive and negative frequencies. So a starting example, and there's two examples on the worksheet that I gave you today. Starting point is three terms in our signal, a DC plus two cosine terms. And if we use Euler's inverse identity, we would expand each of the cosine terms up into a pair of complex sinusoids. So we would group them up pairwise. So first off, or the first thing is to make sure you can see how that's coming together, or actually being torn apart. The 5 stays together, obviously, because it's DC. It doesn't expand out into two terms, but the cosine breaks apart into an e to the plus j and an e to the minus j. So we get a total of 5 terms, and then those are the 5 locations in the frequency axis where we'll make the spectral plot. So now the question is, how do we do that? We just draw one-to-one relationships in the plot from what we see in this equation 3.5. I've created a tool in MATLAB. I have one in Mathematica that can do it. But when you have to do it on a quiz, you just have to sketch it out on paper. So if we take this example and extract the parameters out into these pairs, frequency amplitude pairs, we have at 0 hertz we have an amplitude 5, and then at 50 hertz we have an amplitude of 3 over 2, which is the 1.5, and then we have the phase of pi over 8. And then at the minus frequency, minus 50, and that is because of the minus sign in here, we have the same amplitude of 1.5, but then we have a phase of minus pi over 8. It's always going to be equal and opposite from the phase at the positive frequency. And then the same holds true for the second, or the last pair. The plus 300 has an amplitude of 6 over 2, which is 3, and a phase of pi over 2. And then the minus 300, and this is a typo in here, this should be inside of here. The minus 300 is got an amplitude of 3 and a phase of minus pi over 2. Does anybody get that? This is no scroll up or down.
Yeah, I just want to see the original. In the book, they have it where it says like 3 cosine of 2 pi times 50 times t. When they they apply the inverse
Euler
formula, their frequency is divided in 2. So their example has 14 cosine of 200 pi t, and that turns into e to the j 2 pi times 100 t. It's like all their frequencies are divided in half.
I don't think it's a typo. I think maybe there's something missing. If f is 2 pi, or I mean omega is 2 pi times f, right?
So then f should be.
I think I see what the problem is between the book and what I did. I have the 2 pi already factored out of here, and that's definitely frequency, right, in hertz.
Yeah.
The book may have had if I had omega t equals pi times 50t, what is f in that case?
Should be 25.
It would be 25, right? Because that would factor as to 2 pi times 25 times t. Did they do that by any chance?
Yeah. They have them in parentheses, and then they have the 2 pi outside of it. So
Okay. Yeah, once you factor the 2 pi out, what's left is the frequency in hertz. What page are you on? I guess I had to look.
On page 37.
Okay.
In the bottom right there.
I remember this question coming up before, but
Because then they draw their spectral plot using the divided in half frequencies.
yeah, and that's not right, because that's not physically where the frequency is at. So the bottom of page 37.
Yes.
Yeah, but they have above that, in example 3-1, they have 200 pi t. So that 200 pi t factors out into 2 pi times 100 times t. So that's correct.
Okay.
If everybody else is not following this, they have this term. I'll just pull one of the terms out. 14 cosine of 200 pi t minus pi over 3. And then you could break that with Euler's identity to be 7 e to the j 2 pi times 100t times e to the minus j pi over 3. And then you could add in the other term, 7 e to the minus j 2 pi times 100t times e to the plus j pi over 3. So that's correct, the way I see it. You brought up a good point, though. That 2 gets forgotten oftentimes by people. You'll just make a careless error when you're doing the spectral plot. So the book has the spectral plot on the next page, and the way they do their spectral plots, I don't know, I don't like it. My style is to say we have a phase spectrum and a magnitude spectrum, so I plot them separately, magnitude and phase, whereas the book likes to plot magnitude and phase together to just say it's some complex spectral line there, but that is kind of not a very nice looking plot, because if you were to plot that in MATLAB, can MATLAB plot in an XY plot a complex number on the vertical axis and have a scale next to it? It can't do that. It complains, and some of you maybe have noticed this. What MATLAB will do, if you try to make it plot something complex, say t, comma, a complex quantity, what it will typically do is it will give you an error message, and it will say ignoring the imaginary part. Has anybody ever seen an error message like that last Friday? What is that? When you see an error message or a warning, what do you think of? I mean, if you're driving your car and a dashboard light comes on, what are you supposed to think of? Pay attention, there's a problem. Maybe something's going to break on my car if I don't get it into the repair shop. So MATLAB will warn you, but then it goes ahead and creates a plot, and it might be really bogus. You know, it might give you a warning, and it might look like a nice picture, but it might be totally wrong. It's not totally giving up on creating a picture. It's just saying, I'm ignoring the imaginary parts. So I go with the magnitude and phase plot, and the reason why I go with the magnitude and phase plot also is because when I show you the spectrum analyzer, when I bring in some test gear, either this Friday or a week from this Friday for another demo, you'll see the spectrum analyzer displays the magnitude spectrum. It doesn't display the phase spectrum, typically. So usually when we're doing analysis, we have both available. When we're doing measurements, we generally just have the magnitude spectrum available, and that has to do with the way the measurements are taken physically. The combo things are something that the book has, but I try to suppress that. I can't keep you from reading it. I'm just going to force you through the examples and things to look at it as the magnitude, which is the magnitude of the complex coefficients, and then the angle is the angle of those complex coefficients plotted versus frequency. So at any rate, now that we have all the pairs in here, let's see, can't do that. Can do this, nope, can't. When I run this in my office without the tablet, I can do different commands. At any rate, we have, clearing away some of this clutter, we have 5 pairs in here that we need to plot. And I wrote a function in MATLAB called line spectra, which allows you to automate that. This is available on the website. And I guess now that I'm doing this, and I've done this a few times, where do I keep things like that if I don't link everything? Some of you probably have figured this out, but some of you probably haven't investigated. If you go under this first tab called Course Materials, at the very bottom there's this link called Lecture Notes, and this is what's going on behind the scenes. This is like the file listing of that particular folder on the web server. So here you can see everything. A lot of this stuff is linked to the web page, but sometimes I don't have links for everything because that just clutters things up. So you have to go. It's worthwhile at times to go rummaging around in here. You'll see some things that we haven't come to, like last year's version of the midterm review, but it's available. Rotating phasor, some of the other little examples that I go through are in here. The line spectra one should be in here somewhere, unless I pulled it out, which I don't think I did. Yeah, line spectra example. Yeah, line spectra zip. This has got the M code in it that we were just looking at. It's inside of here. The web server doesn't let me put a .m file on here such that you can right-click it. It's thinking that could be dangerous. So if I put it inside of a zip, then it's safe to go grab it. So if you want it, just go save target as, and you'll have a copy of it. So without listing all that stuff or spending time on the details, you can study how the function was created as an example of function writing in MATLAB. But I used it just to create pictures. So the bottom line is, if we go look at what those frequency amplitude pairs were, this spectral line right here corresponds to the 0, 5, and this is the magnitude plot that we're looking at right now. And then we had this spectral line corresponds to the pair that was 50 hertz, and the amplitude was 3 halves. And then this is its matching guy, which is at minus 50, comma 3 halves. And then this is the one that's at 300, comma 6 halves, and so on. This is very non-mathematical. I mean, it's just making associations and drawing a picture. So we're going to look at the example sheet here in just a couple of seconds, making sure that you're kind of getting the hang of it right now. But if you just go back up here and see how we identified, the hardest thing is just making the identifications. We start from the x of t right up in here, and then you have to identify. So in the beginning, you go down here and you say, okay, it expands out like so, but ultimately you don't even have to go down to that second writing of x of t. You can just pick everything off that you need just from here by inspection. And let's just talk about how would you do that. If it's the DC term, it just goes at the DC location with its amplitude, which is 5. If it's the 50 hertz term, what is that cosine from Euler's inverse identity going to do? It's going to separate into 2 terms, right? So what are the 2 terms that it goes into? Yeah, into a plus j and a minus j. But we know we're going to have a spectral line at 50, and at what other location from that cosine term? 50 and minus 50, right? Is that obvious enough from Euler's identity? It breaks apart. And then what does the amplitude do? The amplitude starts out at 3, but because it's going to get represented as a spectral line both at 50 and minus 50, a good way of thinking of it is it has to get split. If the amplitude gets, half of the amplitude's at plus 50 and the other half's at minus 50. And that's right here from what Euler's identity does. It puts that factor of 2 in there. So we get an amplitude of 3 halves at plus 50 and an amplitude of 3 halves at minus 50. Now what about the phase? The phase doesn't split. The phase just simply becomes its natural value at plus 50 and then its conjugate phase, which is in this case minus pi over 8 at minus 50. And again, that is what is falling out of Euler's identity. And make no mistake about it, you have to understand that that right there is the expansion for that, and we get our spectral representation from the Euler's inverse identity. But once you've done it a few times, it's not a particular difficult exercise to just do it by inspection. So we have a 3 halves at plus 50, we have a 3 halves at minus 50, and then we have a pi over 8 at plus 50, and then because of the minus sign sitting out here, we have a minus pi over 8 on the phase plot at minus 50. Kevin?
Is that 2 pi times 50t, is that the frequency?
That's the frequency in radians per second, but we're choosing in our spectral plots to plot on the frequency axis in hertz. It's arbitrary, but again, electrical engineers like hertz for the spectral axis because it relates more to the physical world, or at least the way I think of it as when you're tuning a radio, and these days with digital tuners, you've lost the full appreciation for that. That's part of my generation with the mechanically tuned radio. I bet there's not very many of you even know what I'm thinking of when I say mechanically tuned radio. Does anybody have a radio that tunes mechanically?
I know, like the knob.
Yeah.
meter on early.
Yeah, a little dial that changes locations. Do you have any idea what's going on inside the radio electronics when you're actually moving that knob? Okay, take a shot.
Based on the coil. Based on the coil moving up and down, it increases the tunes it in the frequency.
It's actually more typically not changing the coil, it's changing the capacitor. You've got a tank circuit, as it's called, a resonant tank circuit composed of inductor in parallel with a capacitor. Generally, the inductor stays fixed, and the capacitor is what you're changing. But then came along, rather than mechanically tuned capacitors that had fingers on them and plates that came together mechanically. Has anybody ever seen a capacitor like that? Where there's a set of plates that are kind of semicircles that engage and then disengage. And, you know, from physics, a parallel capacitance is what? Should be like in your brain, maybe. 3 terms in it. C is epsilon A over D. Does that formula sound familiar? Epsilon is the epsilon naught times the relative permittivity times A is the area of the plates that overlap, and D is the separation. Does that sound foreign? Okay. Well, then what came along after the mechanically tuned capacitors, which was actually the knob was changing how those plates open and close relative to one another. Then we had electronic capacitors, which is made with something called a varactor diode, or variable capacitance diode, which is a semiconductor device that you change the reverse bias on the device, and that changes this depletion layer width so that you basically have an electronic version of the plates of the capacitor moving further apart as you put more reverse bias on, or closer together with less bias. It's all based on the same formula, though, epsilon A over D, something you learned in physics, right? If you've had that part of physics already. How many of you have had that already? Because I'm not wanting to make sure. Okay, most of you have seen it before. It's amazing, isn't it? I mean, I'm saying because as time changes, what you need to know at one point in time is different than what you need to know at another point in time, because now we moved on and we do things differently. But that's how we could change the frequency, and you can build an oscillator that way too, that you would tune the frequency of oscillation by changing capacitance. So what do you think? Is this sort of making sense? Or the hardest step is to get these frequency amplitude pairs from the original signal. I guess maybe it's just time to jump to the example I handed out and take a crack at it. Does everybody have one of these sheets that I passed out? Okay. So the first thing we have to do, we could do inverse Euler's identity on all of this if we wanted to. I would like to avoid that, but if you want me to step through it, I would like to be able to just say, okay, can we get the amplitude or the frequency amplitude pairs just by thinking in our heads what inverse Euler's identity is doing. The danger is you might not get strong enough with Euler's inverse identity. I mean, practice makes perfect, right? But for drawing the spectral plot, and this will be the basis of the quiz on Friday, hopefully now you're seeing a theme that I've learned over the years of teaching this class. I try to have these example sheets, this type of problems embedded in the homework, try to drill on it some in lecture here, and then you get to demonstrate on Friday how you're doing with it. And then, of course, all of these things are the types of problems that show up on the midterm, along with some of the other lesser sophisticated things. This is like a core topic, though, the spectral plots. So rather than having you break into groups right now, let's just try to work this out. If we wanted to get the frequency amplitude pairs, so I'm just going to say the pairs corresponding to this signal are, because once we can get these, then we're good for plotting. So I'll just use a curly brace. the first frequency amplitude pair is the DC term, right? So what should that pair look like? 0, 9. Then the next one in our collection should be corresponding to this term right here. And we know from inverse Euler's identity that's going to break into two terms, right? Two pairs, right? So what's the frequency that we're at? 440 hertz. Does everybody agree with that? Okay. So we have a 440. And what's the full complex coefficient that we would have inside of here? This would be like our x1, if you want to think of it that way. Okay, we have a vote for 12e to the minus j pi over 4. Ask questions if you don't follow. So you have a question? You're concurring, you're voting? Okay. Anybody else disagree or anybody else agree?
Is it positive j or negative?
It'd be negative.
It'd be negative. Because when we use Euler's identity, this is a good question. If we were to do, let's just make sure we understand Euler's identity. Let's go down here and do an Euler expansion on that. We would go 24, and then if I was doing it by the book, the book would say e to the j theta plus e to the minus j theta. When I say the book, I mean the trig identity stuff. That's what that cosine breaks down into, e to the j theta, which is the entire argument, plus e to the minus j theta. So if I would do that for this term, I would have e to the j 2 pi times 440t minus pi over 4, and then I would repeat that over here with the minus sign out in front. Divided by 2 everywhere, right? So now going back up in here into this first term, the first of two pairs that correspond to 440, the 440 hertz cosine wave, I would have 440, and then we were saying it would be 12, which is the 24 divided by 2. And I'll just switch colors here in midstream. Then that's not what I wanted to do. We have to add in the e to the j term. E to the minus j pi over 4. And that's so because of the fact that if I look at what that term is when I factor it out of the e to the j 2 pi 440t term, I factor out an e to the minus j pi over 4. Agreed? That's how that factoring would work? Because actually that coefficient x1 comes about by saying, okay, I've got 24 over 2 times e to the minus j pi over 4, and then I have the rotating phasor part, e to the j 2 pi times 400t. So that's the x1 right there. Because I haven't done anything funky with the math, like all of a sudden put in a sign change. Everything is totally reproducible. The e to the minus j comes factoring out, so it has to be part of the x1. So we don't really need this anymore. Now we can just say, what's the next one going to be? And let me do something, clean up some of my dust. If I can manipulate my mouse around here. I didn't get it. So much for cleaning things up. There we go. Okay, so the next one is the minus 440. And it just follows suit from the first one, because what is that next amplitude? It's the okay, which is the conjugate of the first one, right? Okay, now going from the second term that we have in here, what's the next term? It's the 14 cosine 2 pi 5,000, right? So what's our frequency on that term? It's 5,000. And then the amplitude is, okay, 7e to the j pi over 8. I'll just ask Kevin, since he asked the question before, does that follow from what happened before? We carried the minus pi over 4 down from that first cosine term, so now the second cosine term has the plus pi over 8, so we'd be carrying down the j pi over 8.
So the next one will be negative.
Yeah, negative 5,000, and then 7e to the minus j pi over 8. Now we have one term left, and this is a sinusoid, a sine as opposed to a cosine. So let's see if you get this one right or figure out what's going on. That's at 8,000. And remember, we always have to get everything in the same basis, so we want to get everything in terms of cosine. So in order to make this look like a cosine, what does this actually become up here?
Minus pi over 2.
So we'll have to put in an 8. I mean, we can just think in our head, but it's a 2 pi times 8,000 times t minus a pi over 2, right? So that becomes 4 e to the minus j pi over 2. And the last one's going to be minus 8,000 4 e to the j pi over 2. So now we have the elements that we need to draw our spectral pictures. So I'm just going to say magnitude of x as if to say the magnitude spectrum associated with the signal x of t. And what are we going to have for our spectrum? If we think of all these pairs, all of these pairs now that we have in the curly braces are spectral lines, which are vertical lines on this plot, to give us a notion of where the spectrum has got energy in the signal. So we have a spectral line at 9. Sometimes people might just put a little ball at the top of it, so that would be at 9. And then the amplitude at 440 is what? That's 12, isn't it? So I've already messed this up. I didn't draw my scales too good. That's why I made the program on the computer to have it draw it for me so I could make it look neat and tidy. But of course on a quiz you got to be able to do it yourself. So we have 9, then we have 12. Amplitude of 12. What location is that at on the frequency axis? Then over here we have a minus 440. We got 2 more pairs to go, right? So where's the next pair at? Plus and minus 5,000, right? My scale's not going to be totally accurate here, but we've got something at 7 at 5,000. And that's at a height of 7, 7. Then we have a 4 at 8,000. So the idea of having this magnitude spectrum plot would say, if we looked in the time domain, we'd just see some scrambled up looking wiggly repeating waveform, perhaps, but we wouldn't necessarily know what the frequency components are unless our ear was really good. But when we look at the spectral plot here, we can see, oh, we have a DC offset of 9. We have a spectral component at 440 hertz, one at 5,000, and one at 8,000 hertz. Now, if we wanted to do the other plot that has to go on this page, and that would be the angle plot, then we're pretty much just going to repeat everything in terms of the frequency locations. But now we need to plot it as the phase angle. So the angle associated with this DC term is 0. Now here's a trick, and this shows up on the next page. What happens if the DC was -9 instead of 9? What would be, how would I have done this plot differently if it was -9 instead of 9? That's part of the example on the next page, which we're not going to do today, but what do you think? In terms of a polar representation, how would you write -9 in polar form? Think of the complex plane. When you have a number that's purely real, but it's at a minus value instead of a positive value, what angle is associated with that negative number? And if we plot it in the complex plane, 9 sits over here, -9 sits over here. So what's in polar form, what's that angle? It's plus or minus pi, right? Because you can get there either way. So if we have a -9 for the DC component, which means we're lowering the signal down by 9, then on the phase axis plot, we're going to have to put a line at the DC location of either plus pi or minus pi. It can be either. It doesn't matter because they're equivalent. Sorry if you like perfection, but you have two choices and they're both correct because you can look at it plus or minus pi. That doesn't apply here, though. It does apply to the example on the back side, though. So in terms of phase angles, getting back to where we were, we have at 440 we had minus pi over 4. So this one has to hang down here at, oops, I'm just going to pick a better color. That's minus pi over 4. And because of the way Euler's identity works, what must be true of the minus 440? It's got to be the opposite, right? So it's going to be sticking up here. And then at the 5,000, we're at pi over 8. And then at the minus 5,000, we're at the opposite, minus pi over 8. And then we are up at minus pi over 2 on the plus side for the 8,000. Oh, yeah. Oops. My eraser works funny. I can draw with it, I just found out for the first time. So that would be the complete magnitude and phase plot then. And as I've said, most of the time the amplitude or magnitude plot is what we're really interested in. And a lot of it has to do with the way instrumentation works. Phasing of the sinusoids is going to give them a different sound to our ear. That would be part of the timbre of a note, let's say, that's composed of all these harmonics. but the amplitude is what we're generally more interested in. What is the strength of each of those underlying frequencies that make up the signal? Does anybody have any questions? Yeah?
The first part of the question says to find the fundamental frequency.
Yeah, good question. We have to get to that. I talked about that when I jumped way ahead in the notes a little bit, but remember what I said last week, what the fundamental frequency would be? Greatest common divisor. Let's just see if that's true. Let's do it for this problem, and then we'll go look in the notes and see if that coincides. So what are the frequencies present in this signal? So F naught, we'll call that our fundamental. That would be the GCD of, we have a 440, we have a 5,000, and then we have a 8,000. So what is that answer? Does anybody think? Pardon me?
Is the Euclidean algorithm or whatever that you learn in discrete math for learning.
Okay, I'm glad you have a name for it, because I didn't know there was such a name as that, because I'd never had to take discrete math.
They like break it. It's just a fast way for a computer to solve for GCDs. It's an algorithm.
It's available in MATLAB with the function named GCD, and in Mathematica with the function named GCD. I believe it's 10 hertz, though. Does anybody? And it's available on the TI-89 with GCD as well. I'm not, like I said, the TI guy that was here today is the real TI guy, the guy that deals with electronics and the circuit stuff that we use in EE. It might be 20.
20 divides what?
Yeah, 20 works, but what is the greatest thing?
No, that's okay. Let me get this bigger so we can see it better. In yeah, there it is. Okay, but I didn't remember in Mathematica whether it was G, lowercase c and d, but it's GCD of, have to put in a list, 440, 5,000, 8,000.
It's 40.
Wait a minute. Maybe that's not the name of the function. That's not what I was looking for. No.
You have to use the square brackets.
Yeah, I don't want to have a list in there. I put in the list, and it did the GCD of each of those simple lists of numbers. So it said 440 GCD is 440. So I see it was basically doing the correct thing, but I just used the wrong calling syntax. 40. So then you would do something like, if this is my list of 440, 5,000, 8,000, and this would be like a vector in MATLAB dividing by that 40. Those numbers there would be what we call the harmonic numbers. The 440 hertz is the 11th multiple of 40, which would be the 11th harmonic of the fundamental. And the 5,000 is the 125th harmonic, or 125th overtone, if you're thinking in terms of music, of the fundamental. That's, yeah, 40 is in hertz, and these guys in here are integers. Those are integers. That's just what number times 40 to get you back to those individual frequencies. That's another concept that we haven't quite gotten into yet, but let's scroll on down here and see. Where we're at. One of the things that's in here that I'm not going to really spend much time on, the book introduces it. They just say, because we're always dividing by 2, why don't we just always take the coefficients to be 1/2 of the original amplitudes? then you can get this representation. This comes up more when we get into Fourier series, which is a little bit later in the chapter, so I'm not going to really dwell on that. The beat notes was the next idea, which I'd like to get back to and maybe run a demo of that before we leave, but skipping over beat notes, periodic waveforms. This is where the discussion of signals composed of multiple sinusoids, which is what we've been talking about. What makes these signals periodic? And what page am I on? I'm on page 13. What makes these sinusoids periodic? It's finding some t-naught such that the waveform equals itself when shifted by t-naught seconds. The smallest t-naught that does that. So the smallest t-naught that does that is the largest frequency that works in the formula, and that's what the GCD is. The greatest common divisor is the same as the smallest period. And we were just doing an example that had 3 frequencies in it. And the general formula is talked about here, where you just say the greatest common divisor of all of the frequencies. And if you have an irrational number, what happens? Does it break? It does break if you have an irrational number. Or at least if you have a real number, I guess is what I should say. And that's something that we looked at briefly last time. And in practice, where does this show up? Well, in practice, this sort of idea comes into play really in digital systems a lot, where you have a waveform that's coming in, and then you resample a waveform. And we'll get into this in the sampling theory chapter. But the clock that resamples is asynchronous. And in most digital hardware, the clock is generated from a crystal oscillator, but there's no reason to expect that that crystal oscillator is synchronized with an incoming signal. And that's where you get this asynchronous, aperiodic behavior from sampling. I'm getting ahead of the game right now, but that's something that wasn't so obvious when I was in school because we didn't have all this digital clock stuff going on. Now everything is digital based, so we have clock oscillators, and they're never perfectly synchronized with another clock oscillator unless we use something called a phase lock loop to make them lock up. So what I want to go back to now, though, is this beat notes idea, and this is what you're going to be doing when you get into the very first thing you're going to play with in the lab is a GUI written in MATLAB called BeatCon. It sounds like a game or some strange something or another. I don't know exactly what to call it. I'm going to close out Mathematica and get MATLAB started here. A beat note occurs when you've got multiple sinusoids present, in particular at least two sinusoids present. And the terminology the book comes up with beat note is based on music theory. When you're trying to get 2 instruments to play in tune and they're not quite in tune, you listen to that and you hear this beating sound. So we're taking the case of a cosine at F1 and a cosine at F2 being superimposed, and we're saying that the frequency difference between those 2 sinusoids is this F delta. So if we're thinking back to our spectral plot here, we're going to have a spectral line at F naught minus F delta, and then a spectral line at F naught plus F delta. I'm just showing the positive frequency axis now. So the separation in between the 2 is F delta. And then average frequency or center frequency is the average between F1 and F2. And in terms of modulation theory, something that briefly gets introduced in this same section is the deviation is how much one tone is pushed above F naught and how much the other tone is pushed below F naught. So that's where the, actually this is 2F delta. Got this defined wrong. So we've got a nominal center value in here. That's at F naught. And we're pushed down by F delta and pushed up by F delta. So here's the spectrum drawn out with the MATLAB program with a two-sided amplitude spectrum or magnitude spectrum. If we wanted to examine what's going on in the trig domain, we would see that the sum of two cosines could be written as the product of two cosines. This you might remember as the double angle formula. Remember that from trigonometry a long time ago? The statements that I have filled in here in the middle is special at this point in the learning process because it says that I can actually prove the double angle formula by using Euler's identity and the fact that we know we can expand out using the real part of a complex sinusoid. So this is kind of novel. I mean, in the past, proving a trig identity might have required some work, or my memory of trigonometry and trig identities was, I don't even know, this is how sad my brain is. Did they just give them to me, or did we have to prove every identity? Does anybody in here remember? If they gave them to you, you didn't have to prove each and every one, so you just had them. So, have you ever wondered how to prove them? Or no, you didn't care to? Complex variable theory and the use of complex arithmetic actually in Euler's formulas actually gives us a very concrete way of proving virtually every trig identity. And this, in the case of the double angle formula, those statements in between shows you how to go about doing that. So you might want to just study that and see how the Euler's identity was used in there. It's pretty, it's interesting is all I can say. It was an eye-opener for me many years ago. So the sum of two cosine waves is the product of the FC, the central frequency, times the peak deviation, F delta. And this is a basic application of the trig identity, which says, I guess I don't have it expanded out in here. The one that what I always think of those, if you have cosine of theta times cosine of beta, some of you probably have this in your memory banks, right? It's 1/2 cosine of theta plus beta plus can't cross the page here, theta minus beta. Basically the sum and the difference, right? The double angle. Cosine of theta, cosine beta breaks out into the sum of two cosines, the sum and the difference of the angles. In terms of the beat note idea though, if we have a 100 Hertz centered signal and an F delta of 5 Hertz, we're going to get a signal that when we plot it out in the time domain has this envelope that's moving at the very slow frequency of the frequency difference, the 5 Hertz F delta, and then the high frequency sinusoid average of 100 Hertz is inside of there. Our ear is actually hearing 105 and 95 Hertz. But when we plot it out as a picture, it looks like that. How could I demonstrate that in MATLAB? I could very easily whip it out like this and say, let's make a time axis that goes from 0 in samples at 8,000 samples per second and plays for 2, hopefully not too painful seconds. And I'll define the waveform x to be equal to cosine of 2 times pi times, let's try 440 hertz in this case, like close to what we were doing in the lab, times t, and then times cosine 2 times pi times, let's go with 5 hertz initially. Oops. What I did wrong was I didn't multiply point times point, so I got to put a point in there. I'll put in sound, and I'll divide by 2 just to scale it properly so it doesn't overload the digital audio. And I'll put in, I want to reconstruct it with a sampling rate of 8,000. Hear the beating in there? Now suppose I decided to make that just 1 hertz. Anybody that played a musical instrument in school remembers a band teacher saying, get it in tune. You know, you hear that throbbing effect. You're going to be playing around with these ideas in the lab. If I was to put that up at 10 hertz, then it's not so, it doesn't have that throbbing effect. And if I eventually make it up to much bigger value, like let's say 100, now it sounds more like 2 notes. I'm listening to a chord of 2 notes as opposed to 2 notes that are beating against each other. But when they're really close, you see this type of phenomenon in the waveform. You're seeing the slow beating action, which is what I have dashed in red. And then you have the average frequency, so your brain doesn't discern the 2 tones anymore. It just discerns the average tone, and then it's kind of pulsating up and down. Any questions? Any comments? Comments about the Super Bowl? I was happy that the Packers won, but I'm sure not everybody was. Okay, I'll see you on Wednesday. We'll take a look at the example number 2, but hopefully you can bring that in and have it all worked out on Wednesday.